始了。我叫林永龙，我虽然叫主办人，但是我什么事都没做。那个要做这件事情不容易，我们很多助理还有很多老师做了很多事情。那这个礼拜呢，我们要在这边好好学习 learning 的这个 system， 因为这个是额满，一个月前就报名额满，所以每一个位置都会有人哈，除非他 no show。这个是我教书30年第一次看到这个情形啊。以前办 summer course 都要请老师动员同学，所以我们现在不用动员了，很好。因为是一个礼拜，也是非常 intensive 的这个课程，所以我们每一个讲员呢，我们都给他弹性。原则上，我们每一个slot 75分钟，包含 Q&A， 但中间会有2个slot之间会有 break。所以希望大家在都能够准时进来，这样的话我们可以准时开始。那我们这个课呢，都有 video tap 起来，我们会放在网络上的。到时候你如果没听清楚，还可以再听，或者是以后 educational 的业务也可以。OK， 好 ，I switch to English.
Thank you.
I'm very glad to introduce to you the first speaker of this summer course, Prof.Marilyn Wolf from Georgia Tech. I know Marilyn since I was very young.
Yeah.
And
longer than either of us are willing to admit.
And I think most of the students should read the book on modern VLSI design. At least I use it as textbook when I taught VLSI design course. So I would say the book is very it's a classic, very popular. I think it made a lot of money. So in that sense, she contributes to the success of our IC design industry because many students learn VLSI design the first course in her book. And so she'll be here all week, and you can share with her at your convenience. Okay, so let's welcome Professor Wolf.
Thank you, Steve. It's always good to be back in Taiwan. Let's start by helping me understand background, because I suspect that there are people with different types of backgrounds who are interested in this course. So how many of you would consider yourself hardware people? Okay. How many would consider yourself software people? Okay. How many would consider yourself neural network people? Approximately 0. Okay. Okay, that's good. I'm more of a computing person than a neural network person. So I will look at this topic, how to design neural networks from the perspective of the implementation technologies. Okay. I should have put this down on the slide, but this talk will be broader issues. Then next talk will be on GPUs, the next one on FPGAs, and the last talk today will be on ASICs. Okay? Across these 4 talks, there are some themes that relate to all of these different technologies. We'll talk about numerical precision. We'll talk about memory systems. We'll talk about interconnection networks, and we'll talk about power and thermal behavior. Okay? We'll see that each of these technologies has different characteristics and trade-offs in these themes, and so that's going to influence how we choose what technology to go with. There we go. Okay. So in in this talk this morning, we'll talk about sort of the design space for convolutional neural networks. I'm going to concentrate on CNNs today. I don't have anything useful to say about analog or about spiky networks. We'll talk about numerical analysis for hardware design, and we'll talk about thermal characteristics. Okay? So, with convolutional neural networks, we're of course interested in using them to classify inputs. One major use of these is image classification. You can use it for other things too. Okay. Before we can use the network, which requires that, operates by convolving inputs with some weights and then classification using a nonlinear function, before we can do that, we have to train the network. We have to identify the weights that give us the answers we want. Okay? So, you're running classification using the network. It's computationally intensive. Training is even more computationally intensive, too. And it's arguably a little harder to analyze. Okay, so this is an ultra high performance application. We want to run it at very high rates. If you're worried about cars, you're using this in a car to avoid hitting pedestrians, nice things like that. You clearly need high throughput, low latency. You also clearly need low power consumption because there's a limited amount of power you can draw from the vehicle. If you're running in a data center, if you're helping people spend their money, you similarly have needs for high throughput, and you have concerns about low power consumption. Okay? So either way, no matter which use case you're talking about, we need both high performance and low power consumption. And that's why people are moving to these fancy hardware implementations. Okay, they're doing it both for mobile, embedded applications as well as data center applications. Okay. How many of you have seen this figure before? Right, yeah, so this is the AlexNet network, which was sort of the breakthrough network that showed people how well convolutional neural networks could operate given the amount of training you could do with modern hardware. AlexNet was specifically designed to run on GPUs. In particular, its architecture was designed to run on 2 GPUs in parallel. Okay. Whether this is the ideal application network or not doesn't really matter. It's a well-known example, and we can use it to illustrate some principles. Okay. Other networks may be deeper, more layers, may have bigger layers, different structures, but this is just a convenient handle for looking at some of the things that these systems do. So as I said, this was specifically designed so that they could run training on fit one of these into 2 parallel GPUs. Okay. And use the communication structure between the GPUs to run reasonably efficiently. The fact that it is split across 2 GPUs limits some of the communication. Okay? And this communication cost is a key design characteristic. And this is one of the areas in which you cannot completely divorce the design of the neural network from the design of the software and hardware. Okay. So it has 5 convolutional layers. talk about this in more detail in a minute, but it's doing standard dimensional layers. So the second, fourth, and fifth layers are designed to require communication only within one GPU. So there's no communication between the two GPUs. Okay? The third layer is connected to all the kernel maps in the second layer. So there is communication between the GPUs. We'll talk about this response normalization in a minute. That's just we waiting, and there's one of those between the first and second GPUs. We'll also talk about this max pooling operation, which is basically a downsampling operation. It's after all of the response normalization. It's also after the fifth layer. Okay? So these convolutional networks operate over a limited range. There are also 3 layers that do convolution across all the neurons in the previous layer. Okay, so they require memory access over a much broader range of indexes. They use their own operation for nonlinear across all the layers, and then at the end they have a 1,000-way operation to classify the outputs of these neurons into labels, right? To say this is a cat, this is a dog, whatever you classify. Okay. In some ways, the operations these are doing are pretty simple. You're basically doing 2-dimensional array operations plus some nonlinear stuff. Okay? That's good for hardware design. Means that we have fewer weird decisions going on. This is in detail. This is a somewhat heterogeneous structure, right? But it has a small number of operators, small number of types of things you're doing, and we'll see that you can leverage that in the design of the hardware. It's also doing a heck of a lot of operations. Go back here for a minute. So you can see that, right, for instance, here we've got this 11x11 window. We've got a 3x3 window here, but they're 27 deep. Right, we've got a lot of operations going on here. That's why we're worried about power consumption as well as performance. Okay. So let's look at these operations in a little more detail. When I say convolution, I mean 2-dimensional convolution. Basically, in the case of the classification, we're taking the inputs from the image or from the previous layer and involving them against a set of weights. Okay? The weights are values that we have determined by training. Okay? So, fairly straightforward operation. We will see that in implementing this, the interaction between all these different convolutions we have to do affects the memory system performance and power consumption. So we can schedule all the convolutions in different ways. Fully associative layer is basically this operation over an entire set of inputs, not just a smaller window. Okay? So pooling is a general term that basically recoined downsampling, but it's a summary of adjacent pixels. It's a little unfortunate they came up with a new word for an old concept, but that's life. Right? You can perform the pooling operation using different operators. Different people have used summation. You also use max operations. You can also vary how the windows overlap. You can have windows that overlap each other, or you can have completely separate windows. Okay? So the AlexNet folks use maximum operator. Okay, so they're working over, they're looking over a window, picking the maximum operator and using that as the result. Okay. In order to make a decision, we can't just multiply and add, right? Linear operators are not enough to make a decision. We have to make use a nonlinear operator to say, yes, this is a dog, no, this is not a dog. Okay? And of course, and in these networks, we don't just do that at the end, we do it, we do nonlinear operations at several points. Okay? So different authors have used different operations for the nonlinearity. Hyperbolic tangent, inverse tangent. Sigmoid operation looks like this, 1 over 1 plus e to the minus x. Okay. And then there's this rectified linear unit, which is what the AlexNet people do. Okay. So the choice of which kind of operator you use can influence the accuracy. It also has a big effect on the performance and power consumption. Okay? So the choice of which operator you use is actually important. And people have looked at both how different nonlinearities affect the quality of the result, as well as the size and power consumption of the hardware. Okay? So AlexNet uses this rectified linear unit, which is max operation. The other thing they do is normalize the response at certain points. Okay, so this is the formula here that they use. This is the normalized output here. This is the output before normalization. This is a weight here, and so you see they're taking the square of all of a set of values, multiply them by weight, and then using that to normalize. Okay. The effect, because this normalizes not just over a single column or a single output, but it operates over an area, right? You're summing these over an area. This is a little like lateral inhibition. How many of you know what that is? Okay. If you look at how the visual system in the brain works, there's a lot going on. Okay? This is actually one of my standard rants. Is that having a simple way to characterize the visual system ignores a lot of details, right? So we have a lot of operations, and just as AlexNet has this deep set of operations in order to do look for features at different scales, different positions, different levels of complexity. Our visual systems do the same thing. But our visual systems don't just look deeper and deeper in sort of one location in the visual system. Okay. Now it turns out that in fact we can take the scene before our eyes and it maps remarkably well into the visual cortex, right? You can take the scene and map it spatially onto your brain. and you go at different depths, and you see different levels of detail, different levels of abstraction. But that's not enough to do vision. We also need to look sideways, across the image. Okay, and this is done various points of the neural network, starting with the eye itself. Okay, so not only do we have rods and cones that sense light at different points of the eyes, but there are neurons that connect laterally, sideways, between those sensors. What do you think those are for in the eye in particular? I know it's early. Okay, but think how you feel on Friday afternoon. Okay. What do you think you use these lateral inhibition neurons for in the eye? Contrast enhancement, exactly. Right? So, if this neuron is seeing a lot of light, this neuron sees less light, the lateral inhibition neuron says, I'm going to encourage this guy to fire more, the one that sees more light. I'm going to encourage the guy who sees less light to fire less, which increases the contrast. Okay? So, lateral connections have lots of uses in comparing space. Okay? And this response normalized ReLU operation performs something like lateral inhibition because it's averaging across an area of the neuron. Okay? So you would get a different response if you were averaging across an area of, say, uniform brightness versus an area that was part bright and part dark, for example. Okay, so that's a quick tour of the various kinds of operations that you do inside these networks. Let's look quickly at some of the other networks that have come out, the other, shall we say, design technologies. And this is not meant to be exhaustive by any means, just to give you an idea. Microsoft Research has developed an FPGA-based system. We're going to talk a little more about FPGAs later. In their first version, they basically evaluate one layer at a time. Okay? So if we compare that to AlexNet, and AlexNet is not doing all of these at the same time either, right? Because the GPU doesn't have enough memory or enough threads to do everything at once. But if we think about an FPGA implementation using the last generation of FPGAs, you would sort of start with some inputs, do one layer, right? Do everything for this layer. That generates a set of outputs that become the inputs for the next layer. Those outputs become the input for the next layer, and so forth. The newer generation of FPGAs are big enough that you can do several layers at once. We'll talk more about that. Okay. The UCLA crew, Jason Hong's crew, also did an FPGA-based design. They use some loop optimization theory that's well known from compilers and from hardware design, which we'll talk about later. And their original system, they evaluated one layer at a time also. There's another group that designed a custom ASIC accelerator. Okay. And then there is the Café development system. There are other development systems that will compile with, onto either CPUs or GPUs. How many of you have used Café or one of those systems like that? Okay, so basic operation is on the feature map, right, where we've got a whole bunch of, on a given layer, we have a whole bunch of different sets of features. Each feature is a two-dimensional array. Okay? So each of these feature maps, we can work at different positions, right? But for a given position, we have a set of different maps that we need to operate on. Okay, so this is an example from a tutorial that just shows that these different feature maps are different pixel values, different weights in 2 dimensions. Okay? So we're going to use the convolution operator to multiply the feature maps times inputs. Okay? So as far as just strict operation count, the convolution is the dominant operation. When we look at nonlinear operations, the response normalization, those have different costs that we definitely have to take into account. But supporting the memory accesses and the operations required for this convolution is an important part of designing these neural networks. When we're designing a machine to run these neural networks, whether it be in software or GPUs or FPGAs or some ASIC, we really have to worry about. We have to worry about numerical precision. Okay? The easy way to do things, the way a lot of signal processing people do things, is to just throw numerical precision at it so you don't have to worry about accuracy. Okay? Well, that has big costs. It has costs in hardware, and it has costs in power consumption. If you use more a larger number of bits in your number, particularly if that's floating point, what are the costs that gives you in your hardware? What price you have to pay to not worry about numerical precision? Hardware. Yeah, but what specifically, what types of hardware costs? Well, there's memory, right? Right? So if you think about this feature map, right? If each of these is an 8-bit integer value, that's one thing. If each of these is a 64-bit double precision floating point value, that's a lot more storage, right? Okay? So that means that you're going to need more memory in each of these layers in order to store things. More bits for your numbers also means more interconnection bandwidth required to push things around on the chip. It also means that your multipliers, your nonlinear units, if you're doing a hyperbolic tangent, that's going to require more bits also. And so all of this hardware is also going to consume more power consumption and generate more heat. Okay? So the numerical precision you use for different types of operations is a critical design decision for these networks. And this is one area in which the design of the neural network algorithms themselves is a co-design problem with the hardware. Okay? We care about power and thermal because they actually limit how much computing we can do. We'll talk about this more in a minute, but performance is limited not by RC delay, it's limited by power and thermal. Okay? connectivity and pipelining is going to limit us both in depth and in breadth. Okay, we have a network, we have a system that is both very wide, because we have a lot of these feature maps. It's also very deep, because we need more layers to do more classification, more fine-grained classification. Okay? And this all relates back to our feature map density. How many features can we put in our system, which is going to influence the accuracy of our classification. Okay, so once again, it's hard to separate the hardware design cost from the operational characteristics of the network itself. Okay, so let me tell you a little bit about the, let's start with this numerical precision. We're going to touch upon this later, but I want to give you a framework for thinking about numerical precision. My student Jason Schlesman did this work in the context of more algorithmic video compression, but this is video analysis, but this is basic techniques are applicable in this domain also. Okay, so Jason came up with a methodology for that fits numerical analysis into the overall hardware design problem. Okay? Numerical representations are a key problem in the design of ESP systems. There is a lot of black art. Basically, if you go to a lot of companies, there's a guy who knows how to take a generic, MATLAB kind of algorithm and turn it into hardware or efficient software. We can't totally eliminate the art to this, but we can use some techniques to help us better understand the design process. Okay? So, we start with an application, in this case neural networks. We're going to break it down into tasks, come up with a candidate architecture, and a candidate set of algorithms. We then need to do some numerical analysis to understand how much precision we need. And we need to look at the amount of bandwidth we need for operations and memory. From there we can go into more detail into how to design the hardware, design the tasks, and map them onto the platform. Okay? So there's actually going to be some iteration within most of these steps, but the goal is to minimize the number of times you have to go back through this loop and to have a fairly speed-forward process. We need to understand the numerical properties before we start designing the details of the hardware. Okay. So, accuracy and precision are not quite the same thing. We care about the accuracy of the result, not necessarily the precision of all the details. Okay? So, in general, our images are going to be 8-bit pixels. Right, maybe 10-bit pixels, maybe 12-bit pixels. And in general, our output is going to be, if you're doing classified into 1,000 different sets, that's going to be 10 bits, right? But the fact that you have, say, 10-bit inputs and 10-bit outputs doesn't mean that everything in the middle here is 10 bits. And in fact, when we started looking at this optical flow problem I'm going to talk about, first student I gave it to said, oh yeah, well the inputs, 8 bits, the outputs, 8 bits, so you just need 8 bits. That's not true. Because in the middle, there's some much more complicated stuff. Okay, so the goal is to have enough precision in the middle that you get a good answer out here without over-designing the system. Okay? Okay, so I think the example that is at least closely related to what you're doing in the neural networks is optical flow. Okay? So the Canati-Lucas-Tommaso algorithm is sort of the best known algorithm for figuring out at each point or in a fine grid across the image how the local movement at those points. So here is the initial frame, here's the next frame. So you can see how the person moved, and unfortunately these are not registered perfectly, so it looks like the background is moving. But basically, the person moved. Right? So we can decompose motion into horizontal and vertical components. We see there's some motion around the person. There's some vertical motion there, and so we can decompose that into vertical motion. Okay? And in general, the motion is going to be a combination of horizontal and vertical, right? So we can do that. So we want to find the horizontal and vertical components of the flow. We're going to do that based upon this matrix operation here. The matrix A in the middle here is performed by is determined by convolving the image with this matrix that basically helps you look for edges, right? Because if you have a flat surface, you don't get any motion. Okay, so that's why this convolution step is why the Canati-Lucas-Tommaso algorithm is related, at least, to the convolution neural network problem. Okay, so the KLT algorithm fits into a larger computer vision system, right? So you may want to do some color space conversion. You're probably going to do this in monochrome. Okay? We're going to do the convolution. We're going to do the gradient matrix computation. We're going to do a matrix inversion, which is where most of the numerical problems come in. Then we'll do a vector computation. Okay? So this is multiplication. This is the numerically ugly part here. So how do we know how much precision we need in different spaces? We can look at the magnitude. We can look at the fractional part, and basically run some examples to get histograms of how much value we need. We can also do analysis, basically algebraic analysis, to say, given the magnitudes of the inputs and the operations we're performing, what's the range of the outputs of each of these operations? Okay? So, doing fixed point, even 16-bit fixed point, is not enough because you have this matrix inversion in the middle. Okay? So Jason decided to go with a 24-bit version of an IEEE kind of floating point. Okay, so this requires doing a floating point adder and a floating point multiplier. Okay. How do you do a floating point multiplication? Right. Right, and then you renormalize. Right, yes. And for addition, you're going to denormalize, right, so that the point is at the same position, right, then you'll do your addition and then you'll renormalize. Right? So it's not that hard. You have to make sure you don't mess things up and you have to worry about signs, but it's not that hard. The hardest part is really going to be the inverse operation. Okay? So clearly we have to be careful about the designing these floating point operations, but we also have to understand that this is going to cost us more storage, perhaps in the form of registers, perhaps in the form of memory, and we have to take that into account in our overall design. Yeah. Well, so this is the if you go through some examples, this shows you how much, basically how big an exponent you need, right? So there's a small number of values that need a really big exponent. Okay, so it's sort of a histogram. Okay, so we have involver here, we have multipliers. Here's the matrix inversion. In order to do the matrix inversion, we're going to use a reciprocal. Okay? And then we put that all together to get the final result. Okay? So, basically, the inversion operation requires a division. Standard way to handle this is to do a reciprocal followed by a multiplication. That's why we're interested in the reciprocal. Okay? This uses a particular algorithm for performing the reciprocal that makes use of some tables. Okay? So you're dividing up the value into regions. You're using that to look up inside a ROM, and then you're going to get some different value. You're going to do some XOR, you're going to add them together. Okay? Nice. So this simplifies the hardware in that this is a ROM, which could also be a lookup table, right, and an FPGA, and this is an integer adder. Okay? Now, I'm not a numerical analysis person. My friend Miriam Leeser is. She spent a lot of decades thinking about numerical analysis, so I'm going to use this as an opportunity to plug her vfloat library, which is what we use for some of this work. Okay, vfloat is particularly designed for FPGA implementations, but you could use it for basic designs also. Basically, you can these are hardware arithmetic unit designs that are parameterized with things like numerical precision and number of bits in different fields and so on. They're carefully chosen numerical algorithms in order to make use of so they embody expert knowledge in what types of numerical algorithms are best for given ranges of precision and so on. Okay. As I said, they're all parameterized, so you can pick the precision you want. They also are designed to decouple the denormalization and the normalization so that you can save some area by not doing too many of these things. There may be some cases where you can use several operations and then renormalize. For example, if you have a library that says I'm always going to do, the multiply addition and then do a normalization, you can end up with extra normalizations, which denormalizations and normalizations, which definitely affect the cost of these designs. So this is a very well designed library for floating point operations, and there's everybody I know has very good success with it. Okay? Okay, so that's a framework for thinking about numerical design. Okay? We want to have enough, so this is, we discussed it in general terms. Later on in the day, we're going to apply this to particular operations in neural networks and see what kind of precision we need. But the basic principles are, we want to look at what amount of accuracy we need to get the results that we want out of the network. We want to look at the hardware costs of those. Okay? So now let's spend a minute thinking about power and thermal. Okay? How many of you have seen the burning Pentium videos on YouTube? Well, there are two subgenres, right? There's cooking on your computer, right? There's also your computer catching fire. Okay? The second category is less popular than it used to be because the CPU manufacturers put hardware in that won't let it get that hot. Okay? But you know, power consumption shows up as thermal behavior. Essentially, all of the power we put into the computer for computation comes out as heat. Okay? That's why I'm talking about the two together. What is the basic limit on thermal characteristics? What's called the maximum junction temperature. So that's the temperature right at the transistor. Okay? If that temperature at the transistor gets above 85 degrees centigrade, the transistor starts to destroy itself. Okay? Okay. So at the system level, this shows up as a specification related to thermal design power. And that's because there's a whole bunch of characteristics that that get you from the junction temperature to the operating temperature of your overall chip. Right? But thermal design power is the maximum amount of heat, which basically relates to the maximum amount of electrical power that you consume, that the chip will be able to dissipate. So, in today's world, performance is not limited by RC frequency, RLC frequency. It's not even limited by power consumption. It's limited by thermal power dissipation. Okay? That's true in the mobile world. It's true in a car. It's true in the data center. Okay? So, so let's take a look at temperature analysis as a way to understand power consumption. How many of you have studied thermal power dissipation and thermal dissipation for processing? Okay. Okay, so the simplest way to analyze this is in steady state. Okay, we're not going to vary anything. We're just going to say we're constantly burning this amount of power, and we want to know what the temperature is. Okay, there's an electrical analog to the thermal equations. Okay, so we can use the equations we use for electrical circuits to analyze thermal behavior. So the thermal power looks like a current. The thermal resistance looks like a resistance. And the temperature drop looks like a voltage drop. Okay? So the ambient temperature is the temperature of the environment. Okay, so in the data center, we've got a lot of air conditioners running. We have water cooling, right? That at least to a first approximation, give you a constant temperature. That's not really true, but let's assume that, right? In a car where you've got all your neural networks running, you have an ambient temperature too, which may be hot if this is under the hood, but let's assume a fairly constant temperature. Okay? So think of that as like a ground. Okay? The thermal dissipation results in a temperature rise. And so the temperature up here is the temperature of the device. Okay? We want to make sure that stays below 85 degrees. Okay? So the temperature drop across here is the power consumption times the thermal resistance. Okay? Power consumption we get from the manufacturer. The question really is, how do we get that thermal resistance? And doing it right takes some effort. Well, let's make some very simple assumptions. Right? If you look at a stack of cooling system, you've got a whole bunch of different layers in the system, which amounts to a complex, well, really is an RC network, right? But you've got the chip to the package, right? You may have package to the heat dissipation unit, the heat sink, and you've got the heat sink to the environment. Let's wrap all of that into one number, which is the overall thermal resistance. Okay? So we're going to say that this chip is running 20 watts. Let's say the ambient temperature is 20 degrees centigrade. And let's say that without a heat sink, the thermal resistance from the junction to the ambient is 10 degrees C per watt. Okay? That's a plausible number for what this would actually be. So when you do the math, you find out that the junction temperature of the chip is now going to be 220 degrees centigrade. Way, way, way too high. Okay? So now we spend a reasonable amount of money on a heat sink, right? Even a halfway decent heat sink will get you down to a thermal resistance of something like 1.5 degrees C per watt. Now the temperature at the junction is 50 degrees C, which is within our bounds. Okay? So for a first cut, basically we know the ambient temperature, we know the power dissipation, we find a heat sink that has a low enough resistance that it keeps us below our thermal bound, and then we ask how much money is that going to cost us. Okay. Now in reality, the thermal output of the chip varies over time as it's doing different things. Plus, the packaging, all the package, the heat sink, all this stuff has not only thermal resistance but thermal capacitance. Okay? So when we take all that into account, what kind of thermal waveforms do you expect to see? Right, they're exponentials, right? Okay, so here's our ambient temperature here, here's our thermal power. We have thermal resistance, we also have a thermal capacitance, right? If there was no thermal capacitance, then the temperature would change instantaneously when, say, we cut off the power, we turn on the power. We know that doesn't happen, right? So we know there's capacitance as well as resistance. Okay? So once again, we can use our standard RC formulas to get the response. Now once again, in reality, real packages are more complicated. They're actually networks of resistances and thermal resistances and capacitances. Okay, but this is enough to give you an idea of what's going on. Doing more accurate analysis is more work, but this gives you a basic idea. Okay? So here's our thermal resistance, our thermal capacitance, power consumption is 50 watts. Right? So let's say that the ambient temperature is 300 degrees Kelvin. We're going to do this one in Kelvin. Then if we turn on the power, we go from 0 to 50 watts, the thermal response looks like this. Okay? So it takes something like 0.05 of a second in order to go up. Okay, and this is where thermal behavior becomes, I think, a challenge for system design. The time constants for thermal behavior are much, much longer than the time constants for electrical behavior. Okay? So even if we think our chip is getting too hot, and we decide to slow it down, reduce the power supply, burn less power, that doesn't mean it's going to instantaneously start cooling down. Okay? So we have to be careful about how we control the heat dissipation so that it doesn't get away from us. Okay? The time constants are very long, and we have to take that into account in our control. But that's another lecture. Okay? This is a step response, right? So we wait long enough, and this temperature basically approaches the steady state value we saw before with just our thermal resistance, right? That was computing steady state. That's where this is heading in steady state. In a lot of cases, though, we turn the processor or the logic on and off. What happens if you do that? Well, we're going to see the temperature go up and go down, go up and go down. Okay, so you'll see this is swinging in a range of 300 to 320 K. Okay. And you see once again that it comes up fairly steeply, but it takes 0.05 seconds to get there, 0.05 seconds to drop. Okay? Now what if we have not just one block of logic, but two, right? So this could be dual processors, this could be different units in our GPU, different units in our ASIC, right? Each one has its own thermal resistance and capacitance, each one has its own power dissipation, but there's also thermal resistance between the two. Okay? Right? So if these were separate chips, say that these are completely separate, right? But now these are on the same chip, they're connected by this thermal resistance, and so heat from one of these is going to travel over here. Okay? And heat from here is going to travel over here. So, oops, sorry. There's a nice little result you can use from electrical circuits to help you analyze this. The question is, what is the ratio between the peak-to-peak versus power consumption, and it actually looks like this, okay, where you have a 50% duty cycle, then this is the time constant. Okay. So red is CPU 1, blue is CPU 1, brown is CPU 2. If we turn one off and the other on, right, we expect them to alternate with this, with these RC waveforms. If you look at the temperatures here, you can see that because the other processor is off, it's pulling a little bit of heat away from that processor, so the peak is a little lower, but also the bottom temperature is a little higher. Okay? So, for a complicated chip, we have to look at thermal behavior in both time and in space. Okay? And there are all sorts of, there are much fancier algorithms we can use in order to modeling systems in order to do that. Why do we care about heat modeling? Well, in the Short term, we care about heat because we don't want our chips to fail, and we don't want some teenager putting a YouTube video up showing how our chips are catching fire. Okay? But in the long run, even if the chips don't catch fire, heat influences reliability. Okay? Running too hot can seriously reduce the useful lifetime of the chip. And clearly, that's important for embedded applications like automotive that require extremely high reliability. In the case of data centers, it also influences the useful life of the chip and how expensive it is to run the data center. Basic principle is that reliability mechanisms are, most of them are chemical mechanisms. Right? There are all sorts of different things that can cause a chip to fail. The transistors, the wires, the oxides, all sorts of things, but they're all chemical processes. And there's this basic law known as the Arrhenius equation that says that a lot of chemical processes, the rate of the chemical process is a function of temperature. Okay? So as the temperature increases, we're going to see higher rates of these processes, which in the case of reliability means that we're going to see failures more often. Okay? So if you run your chip hot all the time, it's going to last for less time before it fails. Okay? And you can think about this as a lifetime analysis. So basically, the hotter you run, the more quickly you're using up your lifetime. So it's sort of, like people, you live a fast life, you run around, you're drinking and smoking all night, and you're eating lots of rich food, you're gonna keel over earlier. You live a nice, quiet life, you're gonna last longer. And one of the things we're working on is using probabilistic models to help us understand this, because these are so complicated that figuring out exactly what's going on is not easy. But we can use probabilistic models, in particular Markov decision processes, to help us understand what's going on. So a Markov decision process allows us to say not just what state are what state is the system in, what probabilistic state, but we can give it inputs and say, well, we want it to do this now, so that's going to run it into this state, whereas we give it a different input here, that it's going to go into this different state. Okay, so now we can say, for a given model of the system, this thermal behavior, for example, we give it different inputs. We go through a different sequence of states, which may relate to its power, its temperature, its reliability. We can figure out the optimal policy, the optimal sequence of inputs that maximizes some objective function. Right? Okay. I'll leave that there. Okay, so in each set of slides, I put just a couple of references. There are plenty more out there, but just so you can look at some of the basic references that we talked about here. Okay, so, yeah, time for questions. Yeah. Go ahead.
Why not RC delay limits the performance?
Wait, turn off the RC is not the limit, the ultimate limit on performance, because thermal limits, the chip melts before you get to the RC delay, right? the thermal limit is tighter than the RC limit. Okay? Okay. So we can't run the chip for more than a couple of cycles before it melts. Okay?
Is there any reference the RCA is much higher? The thermal is much higher.
Depends on how, so the question is, are there any references you can look at for that? It sort of depends on how much detail you want to go into. I just put out a book, Physics and Computing, and thermal is one aspect of that. And so that gives you sort of a, undergraduate level analysis of the time delay stuff and the thermal delay stuff. It goes through some numbers. There are some more detailed research papers that you can go into. But there's also some very interesting websites. Anontech.com does a lot of very good experiments, and they show their methodology. Okay, so they're more on the experimentation side, but they describe what's going on pretty well, and they will give you, real case studies on how this plays out. Yeah.
Question. So among the computing, writing, reading, or storage in CNN, which one has the highest power consumption or sales? Which one contributes the most in peak generation?
Yeah, so the question is, what contributes most to heat generation in neural networks? Is it memory, storage, operations, right? Interconnect. I don't think anybody has done this. That's a very good question. I don't think anybody has done a definitive study on it. But in general, memory tends to be very expensive. Interconnect can be very expensive, and probably the operations themselves are the least expensive, like multiplication and so forth. Right? Now the balance is going to be a little different in neural networks than it is in multimedia, for example, because here the computations are a little more local. So the memory transfers are a little more local. So I actually think there's a little work to be done to fully answer this question. Memory is always the first thing you look at. Okay. Problem is that all these topics, memory, interconnect, and function units, are all tied together through operation, through the numerical precision, right? We pick how big a representation we have for the different values. That's going to affect how much storage we need to do and how much compute we need. The only saving grace is, if we go back to this slide, right? Even if we need high precision in the middle of an operation, that doesn't mean that the inputs and outputs have to have the same precision. Okay, so that's the key to decoupling the function unit cost from some of the memory and internet costs. And I think that may be the issue that some people miss, right? Is they think that I need this level of precision in the middle of my operation, so I'm just going to use it everywhere. But that gives you costs that you don't actually need throughout the entire system. Question? Yeah.
Is a key thermal rating
Yeah.
that page.
Yeah.
And the maximum temperature 85 degrees.
Right.
I think it's a little low. Since it is PM junction temperature, right? So when we create a integrated circuit, the temperature is pretty high. About 1000 degrees. How can the PM junction
So the question is, why is the maximum junction temperature 85 degrees centigrade when we're running at what 1200 centigrade, right, in the fab, right? I'm not a hardcore device person, right? But you know, this is the number that most people quote, and remember that you don't have to. You know, you just have to damage the transistor, right? So when you're fabricating the transistor, you're looking to do diffusions, right, at a certain level and so forth, and you want to do it in a reasonable amount of time, right? You don't want to spend a year doing a single diffusion, right? You know, like spread some boron on it and wait, right? You know, just the Arrhenius equation tells us that the higher we run the fab operations, the faster those will go, right? Whereas, you know, this number is designed to reduce the amount of the probability of damage down to an acceptably low level, right? And that's particularly easy because once you start to damage the transistor, for instance, if it starts to short out, it means you're just going to get more current, which is going to cause more damage. So I think that's the reason that this is at a relatively low temperature, right? It's below the temperature of boiling water. Right? Like I say, I'm not the device person. Question? Okay.
So if no question, then this concludes the first session. Therefore, we have a 30-minute break with coffee. But before we do that, we would like to have a group photo.